Hello everyone, welcome to a tutorial in energy production. This is hopefully one of many tutorials where we'll be looking at various forms of producing energy, both electrical, chemical, and mechanical as well, and different processes and systems that are involved in this. And today we're going to be taking a look at gasification as a method of producing energy and also liquid fuels, because with gasification we also have the ability to produce chemicals. This is going to be hopefully one video of a series of videos in gasification. I wanted this video to be sort of a general introduction to the topic, sort of to get us to think about, essentially what it is if you're not familiar with it. Perhaps this could be a good review video for someone studying for an exam and such. And then hopefully we'll have more videos down the line where we can discuss some of these topics a bit more intimately. So let's jump right into a general introduction in gasification. Alright, so what is gasification? We should start off with a fundamental. Let me just write it out here. It's basically a complex series of steps and reactions of a carbonaceous feed which results in the production of heat and synthesis gas. Okay, so what that essentially means, carbonaceous means a feedstock that is rich in carbon, and we're going to basically use that carbon, break that carbon down through a series of complex reactions to produce a gaseous product called synthesis gas and also heat. So this is done in a unit operation called a gasifier, aptly named, at very high temperatures and pressures usually. Now we'll talk later about different types of gasifiers, but usually it's done at high temperatures and high pressures. Like I said, there's a variety of feedstocks we can consider, a variety of carbonaceous feeds, and we'll talk a little bit about that later. The main ones being coal. Currently, coal is a big gasification feedstock. Of course, there's also biomass for renewable feedstocks. And like I mentioned earlier, there's a complex series of reactions and decompositions that take place. The main one of these being partial oxidation to produce syngas. And syngas is essentially a carbon monoxide hydrogen-rich gaseous product. Now, for those of you familiar with chemistry, the partial oxidation products of any partial combustion, if you will, is the production of carbon monoxide and hydrogen instead of the complete combustion products, which are carbon dioxide and water. So the production of this syngas is that as a result of that partial oxidation or partial combustion process. Now, these gasifiers are run in a highly controlled environment in terms of oxygen and the diluent gases that flow in, and we'll talk a little bit about that later. And so synthesis gas is quite useful because it can be used for the production of fuels. There's a bunch of different catalysts and reactions that carbon monoxide and hydrogen can feed later on. The main precursor chemical, of course, methanol, to a bunch of downstream chemicals can be synthesized from syngas, and of course it can be used for direct power generation. You can actually take synthesis gas and burn it in a gas turbine after you've cleaned it up and you've done something called water gas shift, where you've sort of balanced the ratio of CO to H2. And so yeah, there's a lot of different uses for gasification products. Of course, again, heat from the gasifier can also be recovered downstream. The syngas coming out of this gasifier is extremely hot, and so when you quench it, you can actually recover more heat. And we'll talk about that a little bit detail later on. So let's take a look at the background. I always think it's good to have a background in any sort of process that you're studying. So the industrial origin it's about 180 plus years old in terms of industrial scale. And whether or not they knew it was called, what they were doing is gasification. It was essentially the burning of wood and coal in industrial scales to produce something called town gas in cities, mainly in Britain at the time. And so they would produce syngas or SNG, synthetic natural gas, if depending on the feeds and whatnot. And this helped fire the lanterns in the city, and so they had these networks of gas lines that would run around to all the little gas lamps in the city and whatnot. And of course, something that we need to be privy to is the fact that it's likely more prehistoric than that. Like I said, whether or not they knew it was gasification is kind of irrelevant, but they were definitely using these processes before, of course, 180 years ago. And the main one I wanted to talk about is, early industrial and, of course, pre-industrial is the blast furnace. And, of course, this is involved in production of steel. And of course, steel's been around for a long time, and iron amalgams and mixtures. So this has likely been going on for a long time. And so, in steel production, of course, essentially iron ore, air, and coke, and some sort of fuel is put into a blast furnace, as you can see there on the right, bottom right. And the ore is tapped at the bottom. So once the ore flows through the furnace, the iron is tapped at the bottom, and the gas at the top that's produced from this blast furnace is actually technically syngas, and that gas is recycled back in with air and combusted for heat. So essentially, they had sort of a closed loop. The blast furnace can operate on a closed loop system, where the gasification product, that syngas, is actually burned on site to produce heat, and you'll find that. Even today, that's a main application for syngas in gasification islands. All right, so let's talk a little bit more about this syngas. So, like I said before, it's a hydrogen carbon monoxide rich gas from the gasification process, and this is the partial oxidation reaction in a partial oxidation environment. Now, like I mentioned before, gasifier oxygen is carefully regulated. There are two main ways to do this. You can have air-blown gasifiers where essentially ambient air is just blown into the gasifier, and the oxygen from that ambient air is used to perform the gasification. One disadvantage to this, of course, it is cheaper because all you have to do is compress ambient air to whatever the gasifier temperature is. But you actually will end up eventually, depending on the way the gasifier is built and how it's running, you could potentially produce more NOx, nitrogen oxides, which of course is a very harmful pollutant because of smog, and of course also considerations for acid rain. So you do not want to emit any NOx. So that's definitely a consideration for this. That would mean that the client or the site or whatever would have to implement more cleanup procedures downstream. A better way to do it is actually using pure oxygen blown gasifier, where you would have an air separation unit that would actually separate, usually by cryogenic distillation, nitrogen and oxygen, and that way you could have a more pure product initially coming out of the gasifier. Of course, in terms of capital cost and operational cost, it's a little bit more, but this just goes to show you the flexibility of these gasifications. So let's take a look at sort of the uses of the syngas. So here we have our feedstock flowing in. I'm not going to consider oil at this point, because essentially what they mean is petroleum coke, but I'll show you that on the next slide. So the feedstock goes in, you have your partial oxidation, your gasification, we're producing synthesis gas, and then there's a variety of ways that we can process the synthesis gas if we want to use it for fuel production, liquid transportation fuel. Of course, it can go to fuel cells, but the main routes is that what we can do is we can actually produce more hydrogen, water gas shift reaction. We can use Fischer-Tropsch synthesis, which is we can produce olefinic synthesis fuels generally. And then another main route is a methanol synthesis, and methanol synthesis is a precursor to many of the oxygenates and a lot of oxygen-rich fuels, solvents, and also potentially fuels. So main one is dimethyl ether. You can continue to go down the route to acetic acid, things of that nature. So there's a lot of different uses for this syngas, and of course, as catalysts advance and such, there'll be even more uses down the road that we may not have even realized yet. And so here, I just wanted to write for you what that partial oxidation reaction looks like in its form. Carbon is reacted, and water is also present in these gasifiers. And usually the water is either blown in, steam, or it's mixed with the feed prior to gasification. That's generally what has happened. and then of course you produce the carbon monoxide and hydrogen, the post-oxidation products. Okay. All right, so let's take a closer look at the gasification unit ops itself. There's many different types, and I hope to discuss these more in a later video. But here I just wanted to write down a key thing that I think is important. It's a pressure vessel, so it needs to be designed to withstand not only pressures greater than usually 50 bar, depends on the type of gasifier, but in terms of temperature, it needs to be withstand. I wrote greater than 1,000 Celsius. Usually 700 is the low limit, but generally 1,000 to 1,200 is where the gasifier may be operating. So in terms of the construction, these vessels the metallurgy is key because we need to withstand these temperatures. And it's also key because we need to withstand the pressure, so the thickness of the metal is key as well. And these are not, run-of-the-mill temperatures. These are extremely high temperatures. So that is definitely consideration and probably one of the biggest expense in constructing these. Okay, so, all right, so there's many different types, as you can see below. I put a picture in that sort of highlights 4 of them. And of course, the one that is chosen in any sort of facility is based on the feeds, the process configuration, operating conditions, etc. And another important thing that you need to use with these gasifiers is a quench system, because the gas comes out so hot. If you can imagine, the gasifier is at about 1200 degrees C. And so that gas needs to be quenched very quickly for a few reasons. The main one being helped prevent undesired reactions from happening. The second one is to prevent degradation of downstream equipment, because if you can imagine, if the metallurgy downstream is not designed to handle those temperatures, then you're going to run into some serious problems. So usually after the gasifier, you'll have a heat quench system. Usually it's called a fire tube heat exchanger, which is a special piece of equipment that can generate very high pressure, high temperature steam by quenching the syngas. And that's great because that is another method that allows operators and such to recover even more energy from the process, from the energy that they put into the gasifier. And so here I highlighted, I think generally in my opinion, these are the 4 main types of gasifiers. You have updraft, where the fuel is is inserted at the top, the air comes to the bottom, and then the gas is tapped at the top. Downdraft is essentially sort of the opposite, where the fuel is still put in the top, the air is now injected on the sides, and then the gas is taken at the bottom. And the fluidized bed is where the bed is sort of essentially the entire gasifier is mixed together, and the bed is fluidized. So there's no discrete stages, as you can see on the left. And then entrained bed is a continuation of the fluidized bed, except this time the bed is not spread out over the entire reactor. It is sort of captured down below, and you can see the gas tap is near that entrained bed. In all these cases, you can see that, I know it's maybe a little bit cut off, but ash and slag are pulled out of the bottom. When you perform these gasifications, you have residuals from your feedstocks. Tars are produced, ash is produced, char is produced. Basically, that's spent over carbon, and that is deposited on the bottom, and then that's removed via usually a hopper system. And you can actually, many times you can use that ash. Sometimes they use it, I believe, as maybe they can treat it to make filter-based carbons and stuff like that. They may be able to use it in electrodes and things of that nature, but essentially it's spent fuel, and it can't be used as fuel again. All right, let's take a little look at feedstocks. So as I was saying before, coal is a popular feedstock for gasifiers because it's got a high carbon content. It's easily slurried and pulverized. Sorry, let me finish that. And because of that, and because of its abundance, especially in the United States and also China, coal is a great feedstock to produce syngas. Ideally, in these coal gasifiers, you're going to want to use low sulfur coal because not only is the carbon content generally higher in those coals, but also it will save you cost on cleanup systems downstream, because the syngas eventually has to be, sulfur has to be pulled out because of not only pollution considerations, but also the fact that the sulfur will damage any sort of catalyst downstream in your fuel synthesis section. And sulfur is a well-known catalyst poison. And so anthracite is usually the coal type that's preferred over something. Anthracite has a lot high carbon content, something over subbituminous or lignite coal. Biomass is another good feedstock. Of course, biomass is carbon from organic matter. Usually it's dried. It has a low carbon. Usually biomass, usually feedstocks from biomass, so that being corn or any dried plants, stover from the corn itself, maybe sorghum, stuff like that. Of course, any plant. Wood is biomass, of course. And usually the carbon content in the biomass feed is low relative to coal, something like coal, so you need large volumes, so that is definitely a disadvantage. Of course, it's renewable, so that is a good advantage to using biomass. And the nice thing about using gasification with bio-based feedstocks is that because of the high temperature and high heat and that thermal conversion, it's good for good for feedstocks that are like have very complex molecules, carbon molecules in them. So, for example, like as I gave before, corn stover and parts of the corn that are not the fruit, which are high in lignin and things of that nature, which is a complex molecule that's hard to break down when you use it for any number of direct bioethanol synthesis or biogas synthesis. The gasification will actually usually have a higher conversion of that, so that's definitely beneficial. Another feed that is common in gasifier islands present in refineries is petcoke, petroleum coke, similar to coal. So this is like I said, refinery resids from the refinery cokers or slag furnaces present in a refinery, and it's sort of processed in a similar way to coal. This is a reason why gasifiers are advantaged to have at a refinery, because it can sort of help continually upgrade that bottom of the barrel stuff, right? So where are you getting your cokes from? You're getting your cokes from vacuum gases and heavy oils and stuff like that, and so it helps refineries and petrochemical producers sort of maximize bottom of the barrel, if you will, all the way through, so they can actually have a use for this petcoke. And finally, natural gas. So I don't want to talk too much about natural gas because technically any methane partial oxidation is called steam methane reforming, which is sort of a different process, and you use a sort of a different reactor, although it's similar, but there are different nuances. But I just wanted to put it here just to showcase that it can be used as a feedstock as well. Okay, so let's just look at gasifier up close. So here I put a picture of a downdraft gasifier. And so let's look at the main stages. Okay, so first off, like we showed before, the feedstock's entering on the top, air is blown in at a midpoint section, and syngas is pulled out of the bottom and before an ash filter, and then the char and ash comes out. So there's a few main steps. Of course, first drying. The drying is where the water and the carbon feed are separated. If the carbon feed was pre-slurried or mixed with the water, this is where the water is vaporized and the carbon feed is sort of theoretically separated. Then we have pyrolysis, which, if you're not familiar, pyrolysis is essentially just breakdown of carbon bonds. So large carbon chains are broken down into smaller carbon molecules, and so that happens in a certain section of the reaction. And finally, when the air is injected, in this case, we have our partial oxidation reactions, and then finally reduction reactions. So the partial oxidation reactions, the main ones here being, carbon plus oxygen yields carbon dioxide, and then of course 2 carbons plus oxygen can yield carbon monoxide. 2 carbon monoxide. Sorry, that's a mistake. It should be 2 carbon monoxide. For atom balance, of course. And then you have reduction, which is where you're using either carbon dioxide or water as a reduction. So that plus carbon will yield 2 molecules of carbon monoxide. You can also have water plus the carbon yielding carbon monoxide and hydrogen. And so that's essentially what's going on up close in the gasifier. All right, so let's take a quick look at the process island. So a quick concept check, look at everything sort of on paper. So I know I showed a similar picture of this before, but now we can sort of see where it fits in with the picture of power generation, right? So here you can see feedstock is fed in, the resids chars come out of the bottom. We have our syngas produced at the top. Ash is so after the syngas leaves the gasifier, it has to go through gas cleanup. Particulates are removed. Ash. You have sulfuric acid treatment. Usually that's to pull out the sulfur. Well, sorry, not treated with sulfuric acid. Sulfur is removed, and then usually that sulfur can be used to produce sulfuric acid. Finally, after syngas cleanup, the pure syngas will go downstream, where it's either used for fuels and chemicals, or it can actually feed into a combustion turbine for power generation. So it can be done for both. And also here we have, you see, heat recovery steam generator, which can basically take turbine exhaust. It can also take the hot syngas. Usually that's what happens. The hot syngas also goes through HRSG, and we can make steam and actually recover even more energy. So this sort of concept here is called an IGCC, or as I like to say, the future of gasification, which is an Integrated Gasification Combined Cycle. That's what it stands for. And essentially what you're doing here is you're taking solid material, that carbonaceous feed, you're making liquid transportation fuels, or some sort of, you're using the syngas to make a liquid fuel, and you're also making electricity by combusting a part of that syngas, or using that in or using the hot when you quench the hot syngas, you also generate steam. So you're generating electricity through steam turbines as well. Now I say it's the future of gasification because this system is set up perfectly for such that a carbon capture and storage (CCS) solution could also be placed into this process system. So what we could do is we could easily recover carbon dioxide from either turbine exhaust. If we had, there's a variety of different ways to recover carbon dioxide and sequester it. I'm not going to spend too much time about that because I wanted to make a separate video on that. But as you can see here, I've sort of pulled a line from that clean syngas, and so some of the syngas can go to methanol synthesis, Fischer-Tropsch synthesis, diethyl ether, dimethyl ether, and of course hydrogen could be used in fuel cells, so we can use the syngas directly for liquid transportation fuels, which will meet, of course, the growing demand in our economy for, people want to drive and petrochemical feedstocks and stuff like that, plastics. But also a portion of that syngas and the sheer heat of this system can be used in a heat recovery steam generator and a steam turbine in the same system to produce electricity. So this is truly the robustness of gasification and this Integrated Gasification Combined Cycle, IGCC, that really is the next wave of energy generation, especially if carbon capture and storage is used. Because if CCS is used, then we can sequester almost all of the CO2 produced. Of course, it is more expensive. However, this would potentially allow, while of course you'd want to use a renewable feedstock such as biomass and such, if it would allow us to potentially even use coal, which is a dirty feed, as many people consider, and I'm not too fond of it myself, but it would allow the current infrastructure where we have coal available, coal to be used to generate energy, and all that carbon could be sequestered. So it is a good option. All right. So in summary, we discussed the basic concepts of gasification and the process scheme. We discussed the important, both theoretical and practical, of gasification. We discussed recently the power of the Integrated Gasification Combined Cycle and what it could potentially hold for the future. And so next time, I hope to make more videos, like I said initially. I'd like to discuss more about syngas cleanup and the carbon capture and storage, so that includes, how do we sequester the carbon, and how do you clean up the syngas? How do you quench it? How do you remove the sulfur? How do you remove chloride? Other contaminants, and how do you prepare the syngas for fuel synthesis? talk about the actual reactions that use the syngas to produce the fuel. So that's the methanol synthesis, dimethyl ether, and the Fischer-Tropsch synthesis reactions, the main ones. Heat integration in these process islands, and like I said, syngas quench. And finally, talk about process planning and the current IGCCs. So talk about a few case studies of a few of these IGCCs that are coming online or are already online. So first off, I just want to say, or not first off, but lastly, just like to say thank you for watching. I hope this was informative. I spent a little bit more time than I would have liked, but I think it's a good overview and hope it got you to start thinking about some of the things that are involved in this very powerful piece of process technology. Thank you.